Okay, we're going to go ahead and get started again. Welcome back to part two of the real-world cloud apps with Windows Azure talk. In part one, we covered a bunch of kind of getting started and kind of walking patterns. We're going to start running a little bit more in part two and go even deeper and kind of pick off pretty much where we left off at the end of part one. If you remember, at the very end, we were talking about data partitioning strategies, and I talked about horizontal versus vertical partitioning, and how in a vertical partitioning world, you typically take data and you can split it up across multiple data sources. We're now going to implement this particular partitioning pattern using what's called blob storage. And we use it so that with our fixits, we'll store all of the kind of data around who it's assigned to, when it was opened, the text, the issue, in a database, and then we're going to move our images to be in blob storage instead. So, a little bit about blob storage up front to begin with. If you remember when I talked about the different data storage options that are inside Windows Azure, I mentioned we have three kind of platform as a service options that you can use. For persistence, SQL, which is relational, table, which is a NoSQL key value pair, blob storage, which is unstructured. And the blob storage feature is a really cool one that's pretty easy to take advantage of and delivers a ton of value. At a high level, think of it as a highly scalable, durable file system in the sky. You can store anything you want inside blob storage. You could store movies, you could store videos, you could store documents, you could store text files, you could store pretty much anything. It has a REST API that you can use to program against it. It also then has higher level language wrappers, including .NET ones, that make it really easy to kind of code against. And anything you store in blob storage can either be private just to your applications, or what's nice is you can also optionally expose it over HTTP. And this ends up being kind of really useful where, let's say you want to store images that your app uses, rather than store it to a file system and every time someone accesses the image having to go to a web server to pull it from the file system. You can actually store the image in blob storage and then actually expose the URL to the users directly so that the HTTP traffic is going to the blob storage system as opposed to having to go through your website. You can also control access. So even if you do decide to expose that blob, you can choose who has access to it. And one of the more advanced features that we have in blob storage is something we call short-term leases. And so what you can do is you can actually give a user a short-term lease to access a blob for, say, 15 minutes, at which point their access gets turned off. And so it's really useful if like you're doing a file sharing app or you want to expose downloads of videos or something, you can integrate authorization that's per user and short-term lease as part of kind of the SaaS key that you give out. And that provides a nice way, again, that you can handle lots and lots of storage, do it in a secure way, and we're going to walk through the code for how you do it. So at a high level, with blob storage, you can do a couple things. You can go ahead in the portal, and just like you can create a new website and you create a new SQL database, you can create what's called a storage account. And so I can just go to my data services tab. I could say new storage, click create, and I basically just give it Scott storage account, pick the subscription I want to do, and enable it around the world, or enable it anywhere in the world. One cool feature you'll notice that's built into blob storage, which we'll talk a little bit more later, is this thing called Enable Georeplication. It's just a checkbox you can turn on or off. When georeplication is on, it means that everything you store in your storage account will by default automatically be copied to another region around the world for backup reasons. And so it's done in the background asynchronously, and we basically guarantee within 15 minutes of you writing anything to your blob storage account, we'll basically have another copy of it at least 500 miles away. And shortly, a little bit later this year, we'll actually give you read-only access to that secondary copy. And the great thing about this is it means, if Godzilla comes out of the water and stomps on a data center, or a natural disaster occurs, your data is safe somewhere else. It also means from a DR perspective, or if your storage account is ever having an issue, being able to fail over to the read-only also means that you can actually keep your app up and running, even if the primary issue is just having a temporary glitch. And so you just enable that checkbox, and it'll enable it. One thing that's important about the way georeplication works is it does honor geopolitical boundaries. So if your data center is in the US, it won't copy the data outside the US. If it's in Europe, it won't copy it outside Europe. If it's in Australia, when we open up our 2 regions in Australia, it'll never copy the data outside Australia. So we don't ever kind of set up peering relationships where we back up the data outside of whatever government owns that particular territory. So once you create a storage account, you can then go ahead and programmatically very easily create what's called a container within that storage account. And the code up here basically shows you what you do. Effectively, you just use our .NET API. You can say Cloud Blob Client. You basically just create an object. You point to the storage account. And when you create a storage account, we give you a little connection string. So that's basically where you're getting it there. And then what you can do is you can get a reference to what's called an images container, or I could call this a foobar, or whatever thing I want to store inside my storage account. And then there's a nice code API that says if the container does .create if not exists, which basically means if there's no images container, it creates it. And if it creates one, then you'll notice I'm just setting the permissions on it so that everyone has read-only access to this images container. And you can choose whatever access control policy you want on it. But basically, just by putting these few lines of code in your app, you could also put this in your PowerShell scripts if you prefer to automate it that way. You can now create any number of containers that you can put anything into. How do you store something into it? Well, I have this little helper function that I kind of walk through here that shows you how you could take, for example, an uploaded image and persist it into the images container on your blob account. And basically, again, the same code just connects to the images container. And then what I do is I basically, every time we have an uploaded image, I'm just creating a task photo URL. I stick a GUID in it to make it unique. And I just get the path extension of the file that was uploaded. So if you upload scott.jpg, this will come back as task photo, some random URL.jpg. And then basically, this is the 3 lines of code for me to go ahead and persist that blob, that photo, into the blob store. And you'll notice I'm setting the content type, so I'm maintaining the fact that it's a JPEG in the metadata. And that's basically all the code I need to do in order to upload it into the blob store. And I basically just get back the URL, and I return it from this helper function. Make sense? The beauty is once it's persisted there, I can store any amount of data I want in here. I could store hundreds of terabytes. I could store petabytes across multiple storage accounts. I'm not having to back it up because the geo-replication feature is doing that for me automatically. I can trust that there's multiple copies of my images that are all persisted across different machines. And we, Microsoft, handle and provide the SLA to maintain the data integrity. With that full path URL, I can now give out that URL to my users, and they can basically access that image. Now, in this case here, they're accessing it fully. They have full access to it. If I wanted to, I could also give out short-term leases so that only Joe could access it for 15 minutes. And Fred, I give him a separate lease. He can only access this subset of the images for this amount of time. So if I wanted to, I could lock down exactly the permissions. In this case here, I'm just making it full public. Well, and that's what it's doing from a diagram. We're also going to support full async. The new Storage 2.1 library does support async API support for these storage things, so you can also avoid blocking your web server as you're doing all this code operations. So for our Fix-It app, if you remember, I have an entity framework code first POCO object here with a couple properties. These are all going to be the properties I'm going to persist into my SQL database. You'll notice one of them is called folder URL. And basically, what I have here is if we go to my MVC controller, my task controller, when I go ahead and say, let's create a new Fix-It, and I say, make the bed, blah, assign it to me, upload the photo, hit create. It's basically posting to tasks create, which is this action right here. And basically what I'm doing, you'll notice, is I basically create a new Fix-It task that I'm doing model binding in MVC to populate with the form data. And then all I'm doing is just filling in 2 properties, and additional properties onto that. One is who created it. I'm just using user.identity.name to look up the logged in user. And then you'll notice I have this photo service.upload photo helper function, which is persisting into blob storage and then returning me back the URL. And then all I do is basically just persist it to the database. And this photo service.upload photo, looks like this. And it's basically the exact same code that you saw earlier on the slides. I just basically go ahead, connect to the storage account. I reference the images container within it. I then get a URL dynamically created for the thing I just uploaded, my messy bed. And then that's the 3 lines of code to persist it into the blob store. And I basically just get back the path to it and return it. That's it. The benefit now is my web tier, it's stateless. I can scale out across any number of web servers. And I can now literally store terabytes or petabytes of images in just those few lines of code and scale out my application. And once that thing is actually assigned to me, you'll notice if I click on here and open it up, there's my messy bed. If I actually, how do I do this? Copy the image URL, there we go. That is the URL that was embedded inside my HTML, which points to the image. And you can see basically it's storing it into my storage account. I'm just using the generic DNS. You can also have your own custom vanity DNS, so it doesn't have to surface the fact that it's in Azure. And then you can see there's my images container, and there's that dynamically created URL. So my photo was originally called messybed.jpg. That's where that task photo, we insert the GUID.jpg was inserted. And now my user can basically retrieve that image directly. So very simple way, if you're storing images or music or videos or anything you want to share, definitely recommend using the blob storage. And because we've now partitioned it out, going back to this thing right here, if you think about how much data you have, because we've now partitioned out all the heavy images inside my blob store, I can now have probably 1 million users easily inside my SQL database, inside one SQL database. And all my images in my blob, I could have them actually use terabytes or petabytes of images or documents, and it'll scale out really well. And so that's sort of a simple example of kind of vertical partitioning in use, and using blob store as the back-end system. So we talked a little about data. Let's now move into kind of sort of some of the more fun, advanced stuff, which is how do you survive failures? Kind of the high-level thing to think about in the cloud world. This is true for any environment, but in the cloud world, you're going to find that things fail more often because you're running in a much more distributed system. And one of the things you want to think about, and because you might also have a lot more users hitting it, one thing you want to think about is, given enough time, any app, even an on-premise app, is going to fail. How is your application going to behave when you start seeing issues occur? The network has problems. The dependency that you use has problems. More load suddenly comes in than you were expecting. And there's different, effectively there's 2 ways you can handle it. You can gracefully handle the failure and continue to deliver value to your customers, or you can completely fail and die and tell your customers, sorry, we suck. I highly recommend the first. And basically there's a set of patterns we're going to walk through where you can provide that kind of graceful degraded mode in the case when failures occur. And it's not that difficult as long as you kind of think about some of these things up front. And they can, hopefully the patterns I'll walk you through will help you do it. In terms of kind of the types of failures that you're going to see in any distributed system, but especially in the cloud, I kind of bucketize into 3 types of failures. The first one is kind of machines failing. You'll have cases where individual machines will go down. You're running on commodity machines in the cloud. These are not kind of 5.9 servers with special clustered RAID devices. Part of the reason why the economics of the cloud often makes a lot of sense is they tend to be more commodity-based infrastructure, which saves a lot of money. But it means that as you build your app, you want to design it so that you can handle any of those machines going down. I talked briefly in the website section about how with websites we distribute the service across multiple machines, and we can handle automatically when servers go down. Same is true for SQL, same is true for our blob storage that we just talked about. Under the covers, we're distributing them across multiple machines so that you don't have to think about these types of machine failures as much yourself. If you're running your own virtual machine, though, in an IaaS kind of world, so I just create a VM and I install something on it, you do need to think about this because you have a stateful app that you're managing, and be aware that that virtual machine will sometimes go down. Now, the good news is with Windows Azure, we do have hooks and we do have mechanisms so that you can say, hey, I want to run my database across 2 VMs, and I want to make sure that they're isolated in separate fault domains so that if a whole rack goes down or a power unit goes down, both of my servers don't go down at the same time. And we have built-in mechanisms like load balancing and availability sets that let you manage that. But those are things you're going to want to think about and configure correctly in order to make sure you handle these machine failure scenarios. The other case then that you need to think about, or you want to start thinking about, that happens less often, but you still want to kind of design against it, is when your whole service goes down. So if something you depend on, whether it's the SQL database inside Azure, or a blob storage system, or your website service, or let's say the Twitter service, or some of the external services, or if you use credit card services to do financial payments, something that your app depends on might go down. What do you do then? And this typically happens less often, but you still want to try to be able to gracefully handle it within your application. And a lot of the patterns are going to walk through the rest of this talk. We'll talk about how you handle that. And then the last scenario you got to think about is when a whole region goes down. A meteor comes and slams into the place where your data center is. That is active nature, or there's flooding, or there's a fire, or things like that. So far, touch wood, none of the big public cloud providers, including us, have ever had a complete region natural disaster, act of God thing happen. But statistically, at some point it will. And so one of the things you do want to think about as you build your applications is, what do you do in that scenario? Most of our customers in those scenarios want to make sure they're automated and they have backups so that they could redeploy somewhere else around the world in the case of an act of God thing. If your app is absolutely mission critical and you can have zero downtime, you're going to want to design your app so it's running already in another region and that you can handle in an active way you could fail over. It requires a little bit more work, but it's definitely something you could go ahead and do. I should also mention, in case you're wondering, gosh, this cloud thing now sounds really scary. Any of these things happen in your own corporate environment. You do have machines fail, you do have your SQL databases go down, and believe it or not, a meteor can slam into your building just as easily as it can slam into ours. And so you do need to kind of think about these as well for any kind of existing application that you have. I'm just kind of encouraging you to think about them even more as you go to the cloud. How many people have heard SLAs? It's one of these terms, Service License Agreement, I think. Level agreements. Yeah, I don't even know what it is. I just know I have to meet them. So what does an SLA mean? Well, so basically it's a contract that someone that is offering you a service typically provides and says, hey, I guarantee I'm going to do this. And it sounds really good. It makes everyone feel good. Everyone aspires to do better than an SLA. So the other thing to keep in mind about SLAs is it doesn't mean that you're going to be down. If it's 99.9, it doesn't mean you're going to be down 0.1% of the time. You aspire to 100% always. But typically there is some legal kind of enforcement or financial enforcement around an SLA. For Windows Azure, anytime we don't meet an SLA, you can ask for money back. And we have kind of fixed terms about how bad we violated the SLA, how much money you get back. And so there is an enforcement mechanism in it. What I typically say, though, is the money that you get back almost never compensates you for the impact you might have had on your customer. This is true not just for our SLA, but anyone else's SLA. So, as much as it's nice that you get the money back, it's still, if you have irate customers that were using your app, it doesn't really usually make up for that. So one of the things to think about when you have an SLA is, what does an SLA downtime mean? And so a lot of people heard 99% SLA, 99.9% SLA. A lot of hosters and infrastructure providers love to claim these. If you think about what it really means, though, it might surprise you how much downtime happens when you have a 99.9% SLA, or how much allowed downtime happens. It's 8.76 hours per year is what a 99.9 SLA translates into. And you can see per month and per week. 99.99 is even better. So there's less downtime. You get to 6 nines, and you're basically down to less than a second per week, and less than 30 seconds for the entire year. That's a really good SLA. It's so good that no one offers it. We all aspire towards that. But that's kind of roughly how you translate. Even with a 6.9 SLA, which sounds almost feasibly impossible, you'll notice there's still downtime. There can still be 2 seconds of downtime per month. And so you might think, well, 2 seconds isn't that bad. But if you have an app that heavily depends, you still need to think about what happens in those 2 seconds within your application. A tiny glitch like that can have catastrophic impact depending on how you code it. And if you look at lots of kind of natural disasters or machine failures or things like that, they often start with a small glitch that happens for a few seconds, and then they cascade out and become a really bad issue. So SLAs. So that's what it means with an SLA. So you might be thinking, okay, let's say I use a website, a storage, and a SQL database inside Azure. We each have SLAs. We publish them. Again, we always aspire to do better than this. But you as a developer can say, okay, I'm betting on these 3 SLAs. So what is your app's SLA? 99.9. Anyone think it's 99.95? No? Okay. So 99.9 is the going rate. Anyone think it's below 99.9? 2 people have. Yeah, so this is the tricky thing. So each of your services, so the lowest level SLA we have is 99.9. And if you could synchronize all of the failures to always happen at the exact same time per service, your SLA would be 99.9. But the problem is, typically, your storage system, your database, and your web tier will not cooperate, and they will fail at different points in time. And so what ends up happening is your actual SLA is not 99.9, it's actually 99.75. Because those minutes of downtime can happen independently, they add up, and that's what your app SLA ends up really being. And that ends up being probably 12 hours a year of downtime, which might be more than what you want. And so you might say, gosh, this cloud thing sucks. Don't think that, because you know what? Chances are, if you measure it, you're not actually getting these SLAs anyway in your own infrastructure. But it does mean, as a developer, you want to think about these failures happening, and you really want to code around them so that you can actually survive it. And what we're going to do is spend a couple patterns walking through both. How can you understand when issues are happening? How can you code against them? And how can you get this SLA back up to 99.9 or even closer to those 6 nines that I kind of mentioned earlier. And it is doable, but again, you need to think about it as a developer, and as long as you code around them and get against them, you can make it happen. So how are we going to do this? We're going to talk about a couple different patterns. First one is not really even just a pattern. Well, it is a pattern. It's just having good monitoring telemetry. Actually, step 1 of hitting an SLA is knowing how you're actually doing to begin with. And then we'll talk about some specific patterns about how you can code so that you can handle these types of issues and you can handle failures in a much more graceful way. So step 1, let's just talk about monitoring and telemetry. How many people here have good monitoring and telemetry in their apps today? Okay. How many people know that they probably should have better monitoring and telemetry? Yeah. Monitoring and telemetry, I would say in general, is there's never a state of perfection. It's always, you can just continuously get better and better and better. And one of the things I get to sit through tomorrow, in fact, is a 2-hour meeting with the team every single week where we literally go through monitoring and telemetry data, and we basically inevitably ask ourselves, we should add 4 more tests this week because we missed something that happened in the system, or we found out something later in the system after the fact, and we didn't actually have good source monitoring and telemetry data to tell us what it was. So it's, everyone can get better at this. Anyone here play Frogger way back when? I'm dating myself. Cool game, little frog, get across the thing, things try to kill you, is kind of the summary of it. And you kind of hop around these little logs and you move, and there's like things that come around and you can fall in there. And this is a little bit like running a live service, whether it's an app on premise or in the cloud. And it's a lot easier when you can see the logs and you can see the trucks. Without telemetry and logging, it's kind of like you're just a little frog trying to get across the street, and you have no idea where you're stepping, and you have no idea which truck is going to hit you from which direction. The more telemetry and insight you can get into your app, the more you can actually handle and react when things go bad. So step 1 is get good telemetry. A couple of the ways you can do this. I'm going to walk you through how you can instrument your own code and make it a lot richer. But one of the things I actually recommend is kind of buy, rent your way to victory. There's actually a bunch of good services integrated inside Azure today that'll get you out of the box with almost no coding, in some cases 0 coding, a decent telemetry solution that'll give you a ton more insight into how your app's doing almost out of the gate. And all these things, some of them have free tiers. Most of them cost a little bit of money. What I generally say is the $40 a month it's going to cost you will save you hours and hundreds of dollars and thousands of dollars in developer time when things go wrong. And so these are just a couple examples of them. I'm going to walk through one of them, which is New Relic. Anyone here heard of New Relic? Yeah, cool. They're a good partner of ours. Let me hit our site real quick and do something. Just so I can keep my system updating some telemetry so we can then look at it in New Relic. So I'm just going to, again, upload an image, boom, Go, done. Okay, so we used our app a little bit. What I can do now is go inside the Windows Azure admin tool. And one of the things you'll notice in the admin tool is we have a little icon here called add-ons. You can populate the add-ons by going new store. And our store basically allows you to choose and integrate with add-ons from our partner gallery, one of which is from New Relic. And so if you scroll down here, you can see New Relic. And basically you click next. There's a free tier, and then you can also buy instances if you have lots of paying things. And all you do is basically hit next, choose where you want to deploy it, and then it'll show up in this little add-ons link. And so there's the, oh, that's a different one. That's a Mongo database. New Relic's right there. And so once you do this, you can basically go ahead and grab a connection string. Don't look at mine. But you basically copy and paste that. You then go into Visual Studio. You use the NuGet to install the New Relic agent. As part of that, with NuGet, you paste in the key that you just got from your website, from that connection string, and then deploy your application. The last step you need to do currently, we're making it a little bit more automated going forward, is you also just paste in a few properties into your app settings. And one of the things that I did as part of my automation script is actually set those New Relic settings right there. So I automatically do it when I stand up my environment. And these just sort of turn on the CLR profiler. And what New Relic does is it actually is automatically using the CLR profiler to automatically instrument your app. And basically, once you do this and you start running your application, you can then, inside the Azure admin tool, click the Manage button. This will single sign you on into the New Relic admin tool. And any of the apps that you actually are running inside Azure will now show up here, and you'll start to see built-in telemetry automatically being populated within it. It's kind of like magic. You didn't have to change any code. All you do is sign up, paste in your key, deploy it, and literally within a few seconds, this tool will start lighting up with a bunch of interesting information. For example, you'll notice there are some people in New Zealand that are actually accessing it. You're the only country on the map that is lit up. But so you can basically see where people around the world are accessing it. You can also see what's the average load time that they're experiencing. So New Relic also squirts something in your HTML so they can actually see browser load time and response time, so they can measure it all the way through. And you can also see, how many requests per second, what's the average number of sessions, et cetera, broken up by the world. You can also see, how long is it taking in terms of browser load time. So you can see, how many seconds or milliseconds does it take, how much throughput you're getting, and it'll even score how your app's doing on some standard about whether or not you're fast or slow. So you can also see relative to the world how you're doing. You can also then drill into the app server tier. This is where things get even more interesting. You can actually see all of the actions that are happening inside our MVC app. I can go ahead and click into it. And because it's instrumenting using the CLR, it'll actually even show me what methods are being used inside my server app and how much time is actually being spent in each of them. And so I'm basically getting a full profiler view on my actual MVC actions, all without having to write any code, which is pretty cool. And so if you want to, you can actually drill in, and you can even see kind of what's being called, who's calling what. And if you have an external service, like for example, our blob store, you can even see, hey, we're calling the blob store from within that task create action. Here's how long it took. Here's what the average latency was, and here's whether it was succeeding or not. You can see so far 100% of all of our calls have succeeded. So the cool thing is you get this all by default. You can set up events so that it'll email you when errors start to occur or where memory starts to go above a certain threshold. And the beautiful thing is, again, you don't have to write any code in order to enable it. And so this is sort of an example of, if you don't have any telemetry, enabling this, and there's a free tier you can take advantage of, is just an easy way to get started so that you start to have more insight into what's going on within your application. That's sort of step one. Step two, though, is you're really going to want to also log and instrument within your code itself as well. Once you do that, you can, the more you instrument your own code, the more insight, and the quicker you'll be able to figure out when an issue is happening. Oh, it's because my blob store is down, or oh, it's because blob store latency just increased. And you can kind of start to make much more informed decisions about what's happening. In general, what I recommend when you're building a web app, or building any type of cloud app, or any app in general, is anytime you call another dependency within your app. So anytime your web tier talks to your database, or your web tier talks to the file system, or your web tier talks to Twitter, log it. Log not only whether it was successful, also log how long it took and on every single call. And that basically allows you to say, yep, the database returned, but you know what? It took 2 seconds instead of 20 milliseconds. And sometimes that fact that it was taking longer or faster is more impactful than whether or not it was working. I'd rather a service fail quickly than to take 20 seconds to respond. Because you can, the 20 seconds to respond, your users will be upset and other things will fail. So always measure availability and latency as you do it. And basically always have the logging on. How many people here always have logging on? Well, actually, how many people here use system diagnostics or store things in any kind of log or automation? Okay. How many people that do use that keep it on by default versus how many people turn it on only when there's issues? Most people in desktop world, and I'd say in the ASP.NET on-premise, typically only turn on logging or tracing when they're trying to debug something. What I recommend in a cloud world is always turn it on, 100% of the time. And I'll show you why. One of which is because you can write it to our storage system. Our storage system can store petabytes, and so you don't have to worry about filling up the disk. And so, you know, by keeping it always on, you can always go to the logs when someone reports an issue, and you can always easily pinpoint it. What I have here is sort of example pseudocode for one approach you can take in order to actually log things in your system. It's a simple approach. Basically use the stopwatch class in system diagnostics. Basically say, hey, get a new stopwatch. Go and make your database call. So there's my async call that's happening right here. Once it's completed, stop the time span, and then write to the log and just say, hey, I called SQL. I'm in this method. Here's how long it took. Here's the ID we queried against. Just a simple example. And if an error ever occurs, capture it, and then write the full exception detail to the log as well. That simple kind of mechanism of catching any error, but also recording any success and making sure that you're capturing the time span and how long it took is all you need to do to begin with in order to have a tremendous more insight into your application. And when things go wrong, you can now go straight to the logs and try to figure out what was it? What was the error that was occurring? Or was the latency just going up and down? Was it just taking a long time? Now you know. And if it did take a long time, was it the SQL or was it the blob store that did it? Just the simple pattern instrumenting across your code, you can now capture all of this. You'll notice here I'm passing in an iLogger interface into this repository. You could, for example, use system diagnostics directly and just say literally trace.error and trace.warn if you want to use that directly. The nice thing about using, and I kind of recommend having an iLogger interface that you put in front of system diagnostics, is it gives you more flexibility where if you want to change your logging system later, use a third-party logging system or add some more intermediate data, by having an interface-based logging approach, it just gives you more flexibility later down the road. But if you don't want to do that, you can also just write to system diagnostics directly. And again, I recommend generally put error warning and info level tracing on by default. Always trace, always log it. You might not want to put verbose on, but the other three, it's worth just keeping on by default. Yes, there is some runtime overhead, but no, it won't really cost you in the long run, and it's going to give you tremendous more insight into how your actual system is performing and working. People often ask with system diagnostics, what happens? Is it synchronously writing? No, one of the nice things about our trace implementation inside system diagnostics is it doesn't synchronously write. And with Azure, we have trace listeners that we automatically plug in when you use system diagnostics. And so what we're doing is we queue it up in memory, and then we batch write it in the background of the log system. And so that means you don't have to worry when I did that pattern of writing on each call. You're not actually blocking the user by writing to the diagnostic system. It'll return immediately. Your user will see the results. And in the background, we're writing to the diagnostics log behind the scenes. And what's cool is with websites and cloud services and storage accounts, this writing behind the scenes happens automatically. And we basically can store it for you automatically into our storage system. So let's see a simple example of this. So if we go into our app, you'll notice within my code here, I'm using that same pattern where I take in an iLogger interface. We'll look at what that iLogger interface is in just a second. Every time I do a database call, I do the stopwatch begin. I then make the database call. I then stop it, and I log whether it was successful or not. So again, simple pattern. If we drill into the implementation here, this is the interface, the iLogger interface. Fairly simple interface. And if you look at the implementation here, this is what the implementation of this logger interface looks like. You'll notice I'm just using system diagnostics and basically just passing through to system diagnostics. So there's not a lot of extra stuff happening here. But because it's behind an interface, if I ever want to add more logic, I can now easily do it without having to rip out and replumb my diagnostic system all throughout my app. And then to register this interface, so you might wonder, how does my dashboard controller get it, or how does my task repository get it? It's a constructor argument right now. What I'm doing is I've actually just wired up into my app a dependency injection framework, AutoFac. And so if I go here and loop in, you can see I'm basically using AutoFac, which is a open source .NET dependency injection. And I basically just wire up and say, hey, everyone that expects an iLogger, pass in a logger instance. Anyone who expects an iFixit repository, pass in a Fixit repository, and so forth. And so this gives me a nice way I can unit test, and I have dependency isolation across my application. And that's built into ASP.NET. The AutoFac is a NuGet package with the dependency injection capabilities built in. So now I'm starting to write, every time I write stuff to the log. With Azure websites, if we go back and go up here. If you go to the Configure tab, and again, you can configure this through PowerShell, and scroll down, you'll notice there's this Application Diagnostics tab and Site Diagnostics. And you'll notice we've turned on Application Diagnostics here. I'm writing information level and above, so error warning and info will be recorded. And I basically am just storing it into a storage account. And all of that, again, is wired up as part of those PowerShell scripts when I created it. And now, literally, every time we call a database call, I'm going to have a separate item inside my log store. And so I can go to my Storage Explorer and the Server Explorer inside VS. This is opening up that storage account that my trace system is logged to. And one of the things you'll see is for every time I call my SQL database inside this app, I'm writing a new diagnostic message. Here is a message here, and it's a little hard to read. So let's put it in Notepad. This is an example of one of those calls. You can say, hey, I'm using a SQL database. I'm using it inside create async repository. Here's how long it took, 319 milliseconds to my SQL database to insert it. I just added a task. You'll notice then right before it, I did something else, which is, I didn't do that. Sorry. Copy, paste, not working. Hold on here. Copy. Paste. Fail. Anyway, if you scroll here, oh, it is working, I'm sorry. That's just the end of the thing. Yeah, it is working, okay. My head was exploding. You'll notice this is my blob service call. Coming from the upload photo helper method, it took 135 milliseconds to upload that image and store it. And again, you can see here's the path of the uploaded image. So again, by having all this stuff logged, anytime I have an issue, I can immediately go to this table storage. I can see what calls were happening when the user reported that issue, or when my New Relic agent started saying, hey, the system's going kaflooey or you're throwing errors. And I can basically now pinpoint exactly what my dependencies were doing, how long both of it, whether it succeeded, as well as whether or not the latency was good. And again, it'll help tremendously in terms of pinpointing and locking down issues. In addition to logging application level things, you can also now log HTTP logs from your web server. And so as an example, and it's in that same location inside the portal, you just go ahead and turn on web server logging. And again, you can now point it to a storage system. This just turned on last week. And so as an example, I've done this like for my blog. And now I can actually log all of my HTTP calls and for my website. And basically I can drill into any of these. And this basically shows you all the images for all the links on my old blog posts. I can see their IP address, what they accessed, where they came from, etc. So again, you can log everything and do interesting stuff with it. One thing that's nice is because we're storing it inside storage, is you can not only kind of retrieve it and look it up when you need to, you can also now run analysis tools against your logs. And so one of the other services we have inside Azure, I'm not going to go into detail on how to do this today, but it's what we call a Hadoop service. And so I could go ahead and create what's called HD Insight, and I could spin up a MapReduce cluster on top of my storage account, and I could actually go ahead now and parse terabytes or even petabytes of log files looking for statistical trends. And so if I want to see how is my SQL or my blob storage doing over time, I could actually write a query against it. If I wanted to look at where my users are doing or what my premium users are doing versus my other users, I could go ahead, spin up an HD Insight cluster, and go do analysis. If I want to be really creepy, I could take everyone's IP address that was accessing my blog. I could map it to another data set that's out there in the public domain, which is called per capita per IP address. So I can actually figure out, hey, this person came from a neighborhood where the average per capita income is X. And I could even change my blog post dynamically to try to upsell you features inside Visual Studio, depending on whether or not I think that you have money or not. I'm not doing that, don't worry. But that's an example where, for your own companies, if you want to be creepy, no, if you wanted to be good capitalists, you could. And you could actually start to do some really interesting stuff that you wouldn't probably do in an on-premise environment, but just having that data logged and being able to kind of do the analysis and being able to spin up a Hadoop cluster or spin up other tools that do it, will give you a tremendous amount of insight that you probably don't have today inside your system. So once you have that insight, a couple things you're going to discover. Failures are happening. So the great thing about the sort of multiple phases of the cloud thing is step one is realizing, oh my God, failures are happening all over the place. That's better than not knowing there's failures happening all over the place. Step two is let's handle those failures. The first type of failure we're going to talk about is something called transient faults. These are probably the most frequent types of things you need to think about in any distributed system. This is true even in an on-premise environment, but also in the cloud, which is temporary glitches. The network goes down, the server has a blip, capacity is overwhelmed on a specific service. It might only be for a couple seconds, it might be for a couple minutes, it might be for a couple hours. And one of the things you want to think about inside your application is how do you gracefully handle these as opposed to simply throwing back an error that's happening to the user. There's a couple different ways that you could do it. One of them that we recommend for anything where you're talking to a dependency. So anytime you talk to blob storage, anytime you talk to SQL, anytime you talk to Twitter, is have what's called smart retry logic. So in other words, the pattern is try to access it, try to do your operation. If it fails, retry it. And if it fails again, retry it. Now, you want to be smart about it because you don't want to just continually hammer and retry it. So what you want to typically do is do what's called exponential back-off logic. So this is kind of a simple pattern that Patterns and Practices library has. Basically, it says, in this case here, try doing the database connection operation 3 times and then back off up to 5 seconds if there's a failure. And it will do the automatic logic to kind of figure out, I'll try once, and then I'll try again, maybe 3 or 4 seconds, and then I'll try again after that, up to whatever threshold that you set. And that way, if the database closes the connection or terminates the connection, or a load balancer in between you and the database does it for you automatically, you can basically survive and handle it. The nice thing about EF6 is it's adding this support built into EF. And so all you need to do is basically just add 1 line of code, or it's actually 3 lines of code, into your EF configuration class. And what this you can do the same kind of retry max delay policies where you can say, hey, if the underlying connection in EF gets blown apart, recreate it using the state you already have and try it up to 5 seconds. After 5 seconds, then throw an exception. But this kind of ability to kind of do this back-off logic in a smart way will probably insulate you through lots and lots of different types of errors that might happen in the underlying system. One reason to also think about this in a cloud world is oftentimes with a on-premise environment, you've got a web app and a database that are sitting next to each other in a rack. You typically don't have that many network problems because you're typically just talking to each other through the same network router. In a cloud world, your database and your web tier might be going through 1 or 2 network hops. We try to optimize it as much as possible. But that's why you want to think more about these types of transient errors. You're going to see more of these types of transient errors in the cloud world is because there's more network hops, more network cycles, and you will occasionally see a network load balancer chop a connection for a variety of reasons. And so again, these types of little tricks that you can add into your code will dramatically improve your reliability. I'm not going to show it just because I basically showed the code, but that would basically just, the demo would be showing this 3 lines of code inside the app and how I'm handling it. One thing to be mindful of, which is, and the reason I kind of said exponential backoff, is you want to, and having a max threshold, is you want to be really, really careful when a thing that you depend on starts to back up, that you don't simply throw more and more requests at it. If a service is overwhelmed because it's having a load issue or because it's having a problem with reliability, it doesn't help for you to send another 10,000 requests to it over the next 2 seconds because it just typically makes it more overwhelmed and makes it harder to catch up. Also, likewise, inside your application, if you start queuing up your users and you try indefinitely to keep trying to make that one request work, what ends up happening is your users that get stuck behind the person that's queued just get a great degraded experience. And oftentimes what's better is, try once or twice and then give up and get out of the queue. Anyone here ever been stuck on a flight that got canceled? I have. And I'm hoping to not tonight. But one of the things that you sometimes, that's very frustrating as a passenger is when they say, hey, I'm sorry your flight was canceled. And you go, great, am I on the next flight? And they say, well, not really, because the next flight is booked. But you're on the midnight flight. And you're like, wow, man, why? Bump the person on the 4 o'clock flight. Why do I get bumped at noon? Well, it's because if they bump the person on the 4 o'clock flight, then the person on the 4 o'clock flight then bumps the person on the 8 o'clock flight, and the person on the 8 o'clock flight then bumps the person on the midnight flight, and then everyone's upset. It's better to actually make the people on the noon flight that got canceled unhappy, and then let all the other planes go through, and then figure out a way to integrate them back in there. And that's similar to this back-off logic here, which is if an HTTP request or web page request is going to fail, it's better sometimes to fail fast and have the user just hit refresh, as opposed to making the next 100 users that are trying to hit that page have a slower experience. And that's sort of this back-off. I'll give you an example of, anyone remember when Skype went down a couple Christmases ago? It was actually before Microsoft bought them, I'll point out. But they had a pretty bad outage in the holidays. And the guy who runs Skype and I were at a dinner and we were talking about exchanging cloud war stories and terrible things that have happened. And one of them he talked about was this Christmas outage. And basically what ended up happening was the Skype clients, basically they had an issue in Skype. And the way the Skype clients were designed is they automatically retry. And it was Christmas, so there were lots of users that were online. And what ended up happening was they had an outage. All 10 million, 15 million people using Skype backed off and then retried again. And then Skype was overwhelmed. They couldn't handle it, so they backed off and they retried again. And more people got online and more people got online. And basically they had a giant denial of service attack from their own customers. And the original issue, they could have come back up. But because all of these people were constantly pounding it, they literally had to change the network routing tables so they could bring the Skype service up and then gracefully bring people online, because they were just having these sort of waves of people attacking their own, the waves of their own app with their own customers attacking their own service. And so that's why you want to think about that and be careful about it. Other kind of patterns that you can handle. Distributed caching. So the exponential backoff and the kind of gradual retry will handle temporary glitches. And so if you have a data store in particular, make sure you do that exponential, that transient failure handling. Having said that, though, you're still going to run into issues where either the data might be gone for more than a few seconds, and so it's more than a transient fault, it's more of a persistent failure. And also sometimes you don't actually need to hit the data store on every request anyway, and that's where caching can come into play. It can help you with both of those two scenarios. Sometimes it's okay if you're surfacing weather data or the latest boat racing results from the America's Cup. You guys won, by the way. again. You don't actually, every time someone brings up their app to say, hey, did they win? You don't really need to go to San Francisco in order to pull the results. You really want to cache it. And you might want to update it every second. You might want to update it every minute. You don't actually have to, it doesn't really need to be, immediately consistent. And that's where caching come into play. And then the beauty is if, for example, the service that's exposing the America Cup's data goes down, if you have a cached copy of the data, you can actually implement a switch inside your app and say, hey, you know what? I'm supposed to update it every minute, but for some reason the service isn't available. You know what? I'm just going to wait a couple minutes to upload it until it is available, and my users will probably never figure it out. Or they'll certainly appreciate a cached version of the data more than, hey, we have no idea. So one of the things you can do is take advantage of the new Windows Azure Cache service in order to implement this. It's a new service we just went live with last Wednesday. And it basically gives you a high throughput, low latency distributed cache. It is all in memory, the data, so it's not written to disk. If you have like petabytes of things you want to cache, you might want to use a blob storage system to cache it that way instead. The beauty about the in-memory cache, though, is it's lightning fast. Basically, if you retrieve something from the cache, it takes about 1 millisecond end to end. That includes all the network time back and forth from the web tier or your app tier to the cache and back, which is pretty fast. And when you put something in, it's about 1.2 milliseconds. So it's very, very fast. And it's designed to scale out across multiple nodes. So you can go from 128 megs of cache all the way up to 150 gigs per cache instance. Creating it's really easy. You go to the portal now. You do need to sign up for the preview. And then you go to the portal and you can say, quick create, give it a name, point it in some region, pick the size you want. It's created. It actually takes about 4 minutes or 5 minutes to do this, but imagine it was instantaneous. And then basically you have a dashboard where you can see information about different settings. You can then go ahead and have one giant memory cache, or you could also have what are called partitions, and you can set up different policy rules based on each partition. So you might have some data that expires, some data that never expires, and you have different time frames for each. You can also, and then basically you can get a connection string from it. You then go into VS, you add a NuGet package for your cache library, paste in the connection string information that you got from the portal in your web.config file, and then basically this is all the code you need to write in order to save and retrieve something from the cache. And so basically you create a new cache API, you put a key value pair, you get the key back and you get the value back. And that's basically persisting and retrieving it from that in-memory data source. You can then monitor it so you can see how much memory you're using, how many times you're hitting it, how much compute's there, and then you can scale up or scale down the amount of cache if you need more instances or you need more memory. You can do that all dynamically. And when you scale up and scale down, you don't lose your cache. Well, if you scale down and you have 150 gigs of data and you scale it to 128, you're going to lose up to 100, you're only going to keep 128 megs of your cache. But if you need to scale up your cache, we're pretty smart about adding capacity and not losing the actual already cached items, which is a nice feature that no one else has. And so basically what this means is you can now have your website VMs with auto-scale going against that cache. You could start off, say, with 24 gigs of cache. If you know, hey, we're filling it up, let's add another 48 gigs. Again, you can scale it out. And all of those web servers on all those different VMs can all access the same cache. And so the benefit there is if one VM caches it, the other VMs all have access to it. And that's what makes it distributed. And it basically gives you a way you can scale and cache data across all the apps, or all of the VMs and instances within your application. If you ever use the ASP.NET in-memory cache, the cache API, that's an example of an in-VM cache. That's a great cache, but it would basically mean the data is only stored once inside each of those VMs, and so each VM would have its own cache copy. With a distributed cache, they all have access to it. We're also smart so that if a VM goes down or needs to be upgraded for patching, we can migrate the cached content to the other nodes and then add a new node into it. So we do all the management for you in the back end as well. A couple of cool things you can do with caching as a strategy and as a pattern. A lot of people implement what's called an on-demand cache-aside pattern. This is where your web tier hits the database, grabs the data, and then when it gets it back says, hey, let me cache it, and the next time it checks the cache before it hits the database. If you've ever used kind of like a content management system, like if you use a blog or you do most CMS systems, it's typically using this on-demand cache-aside strategy. So the first time you hit your blog, it hits the database. The next user that hits it hits the cache content. And then after 10 minutes, it resets, and the next guy gets it from the database. And so it's a good strategy you can go ahead and use. Another approach you can use, though, is you can basically say your web tier never hits the underlying data source. So if I was building an app in New Zealand for the America's Cup results, I would probably not have the mobile apps hit San Francisco directly because there's enough people here that care about racing, and since you're going to win it, you might care even more. And so, knowing that, hey, 5 million people might all, with a short window of time, be pounding to see the result race, I don't want to use the cache-aside strategy. What I might instead do is say, I'm going to use a background data push, where I'm going to say all the web tier and all the mobile clients are going to hit the cache always and only, and then I'm going to have a background service that's just running that once a minute hits San Francisco, gets the results, and then pushes the results in the cache. And that way your web tier is always going against the cache. And that means I don't have to ever worry about thousands or millions of users and ever hitting my backend data source. The other benefit about that approach is if San Francisco ever has a problem reporting the data, the users are still seeing the latest copy in the cache. And so one challenge with the on-demand cache-aside strategy is if the cache expires and then everyone hits it, if for whatever reason that service isn't available, you'll have outages or you put a lot of load on there. And then some people also use a pattern called circuit breaker. This is not exclusive to the cache. There's other circuit breaker patterns. But it basically says, hey, if I detect something going wrong in my app, let's just fail over to the cached version. If you've ever used Twitter and you ever see like, hey, I can't go back in time, and it says, hey, sorry, you can only see your top 15 cached items in your Twitter feed. That's an improvement over what they did a couple years ago when Twitter went down. You had the fail whale. Remember that? That was really frustrating. It was cute the first time, and it was really frustrating after that. The nice thing about their approach now is they have a circuit breaker, and they basically discover when they're having an issue, they basically just flip a switch, and the experience gets degraded automatically. It still shows your last 15 items. It still shows a bunch of functionality, but they've effectively turned off a bunch of things, and they've gone into cached mode until the service is healthy again, and then they flip the circuit breaker back, and the system gets back healthy. And so that's another pattern you can use with caching that can end up improving your experience. Anytime your users share a lot of content or where the content doesn't change frequently, cache it would be my top level guidance. It'll make your apps a lot faster, and you'll have a much more reliable system. So caching is really good when you have information that you want to have available even when the underlying service is having issues. So it's great for any read-only pattern. You might be asking, but what about write patterns? So this Fix-It app, it's great. I can cache my list of items, but what happens if someone wants to come and enter a new Fix-It task in the system? How can I do that? And this next pattern, this final pattern, is called the queue-centric work pattern, and it can help with it. Basically, the idea behind the queue-centric pattern is enable more loose coupling within your architecture so that you don't have to do synchronous tasks every time something happens. Instead, what you do is you create what's called a message, you stick it on a queue, and then you respond immediately to your user, and then something picks it off from the queue and then does processing with it later. It's really useful for anything that's time-consuming. It's really useful if you have something that's resource-intensive. It's really useful if you're relying on an external service that might not always be available. And it's really useful if you have a sudden load burst. So if you have lots of people wanting you to do something immediately, queuing's a really good way. You can do what's called rate leveling so that you can kind of handle that and then catch up over time. So what does this look like? Let's take our Fix-It app, and we'll kind of illustrate it. Right now, we have a Fix-It web server talking to our database. This works. But what happens, and we show success as soon as you enter a Fix-It task. But what happens when the database goes down? Well, the web server is offline. You can no longer add Fix-It tasks. And that might be okay for a small application. But if you got a lot of users, they're going to be really annoyed when they can't enter Fix-Its, and they're going to go to someone else's service. Another approach you can do is this loosely coupled approach, where instead of the Fix-It web server entering a Fix-It task immediately into the database when someone enters it, they instead stick it on what's called a task queue. And so they create a little message in JSON, serialize their .NET object to it, stick it in the queue, and then they show success immediately to the user. And so it's never even reached the database before they're telling the user, hey, thank you for your order, we're working on it now. You might be thinking, hey, that's cheating. Yes, and your users will be thankful for it. If you've ever bought something on Amazon.com or Amazon.co.z or any e-commerce service, and you go to check out, and you go check out, and it says, hey, your order's on the way, they just cheated too. This is exactly what they're doing. They didn't really talk to Visa, they didn't really schedule it, they didn't really pull it off the shelf and actually box it all up in that fraction of a second. Instead, they just stuck a message in the queue and said, thank you, it's on its way. And then in the background, they have something that pulls it from the queue, processes it, and updates the database. And now, if the database goes down or the queue listener goes down, you can still be firing orders and messages into your system. Your users are still happy. They're going, hey, this thing is so reliable, it's never down. And you're panicking, oh my God. But when it comes back up, you're going to be able to process those messages, and the user will never know, hopefully, that there was an issue. It's also then useful if suddenly a whole bunch of people show up and they say, hey, I want to order this thing right now. So think of this like the social networking burst or an advertisement on the TV. Everyone goes to the website and wants to buy that thing, or they want to order it or get notified. The beauty is you can now have autoscale spin up as many web services as possible. They're all taking the order, sticking it in a queue, and then your background listeners can slowly catch up. And so you can handle that sudden massive burst because you're not actually doing the expensive work until later, and they can do it more sequentially, and they can actually process it as they have time. A really cool feature about autoscale that we have built into Azure is you can make autoscale work either CPU-based, or we also let you do it by queue length. And so you could actually have worker roles or VMs in the background automatically get spun up as your queue size increases above a certain threshold. And so we can automatically start adding machines to help you catch up on the background if it's a sustained burst. So you might think, okay, this sounds cool, but how do we modify our existing fix-it task scenario to use queues? So remember, this is the scenario. We enter data, we enter a photo, we upload it, we show success. The way it's implemented today, our web tier is directly talking to the database, inserting a fix-it task. What we do in the future is we just replace that one line of code, and instead we fire a message to our fix-it queue manager. All this is doing here is basically just connecting to our storage account, just like we did with Blob. In this case here, we're referencing a fix-its queue, and I basically just serialize that EF POCO object into JSON, and I post it into the queue. Sticks it in the queue, and then on the background I have another VM that's just going to basically pull forever, pulling things off the queue, deserializing it back into that object. And then notice we're using the exact same fix-it task repository that we were using before to save it into the database. And so all we did was basically decoupled that one line of code, the create fix-it, put it in a background role, and then passed it through a queue. And that's basically all we need to do. And once we do that, we get a lot more resiliency. And so now, even if our database is down, we can still take fix-it tasks and show success to our customer. It also means that because we've now decoupled showing the success from the actual processing of the message, if we wanted to add more logic, so for example, instead of just saving it to the database, I wanted to actually figure out who should process it inside my organization, or if I wanted to send SMS messages to notify the person if it was an urgent request, I could start to add that logic in the queue listener without blocking the web tier at all. And you might say, well, what if the SMS service is down? Well, the beautiful thing is I can even do more custom workflows where I could do long-lived operations where I could say, hey, if the SMS system is down, just queue it up and keep retrying until it comes back up and then go to the next step. And so you can really kind of start to orchestrate much more reliable systems by using this queue pattern and then do it for either short or long-term services. So what is our SLA now? Just thinking about this queue service, forget caching for a second. Previously, we had 99.75 because this is for the create fix-it request scenario. So this is not read, this is only write. So this is when I sign up to go and create a new fix-it. Previously, we needed all three of these services to be healthy, 99.75. Now that we have a queue, we only have two services because queues are part of the storage service. So I'm not adding a new service, it's actually part of the same storage service. And so now we're back up to 99.85. And so again, even if the database is down, my app is doing okay. Now you might say, hey, 99.85 is still, 12 minutes a month of downtime, or I think. That's that still seems too much. How can we make it more reliable? Well, here's the cool thing. Storage accounts can be scattered across all Azure regions. So what I could do to actually make this 99.95 is I simply have 2 storage accounts. And so if my primary queue listener is down, I basically go to the backup one. And I literally just inside my code say, hey, try sending here. If it fails, go here. And then I now have 2 storage that are independent of each other. And suddenly now I'm probably close to perfect on that SLA, at which point my overall SLA is now just gated by my web tier, which is 99.95. And if I wanted to be even fancier, I could then have 2 instances of my web tier running in the 2 regions that are independent of each other. And I could use what's called a traffic manager component, so I could actually automatically fail over if my web tier goes down, at which point my app is almost 100% SLA. It's not really 100% SLA. It's 99 close to that 6.9 SLA that we have there. And so, basically it's by starting to use these kind of components, thinking about the telemetry, looking at what's failing, and sort of decoupling it in this loosely coupled way, I can start to add significantly more reliability within my system while still being very cost effective and start scaling it out. And so, as you start doing, things that are more stateful, so for example, there are some operations that are harder to scale. I don't want to make it sound like this is just trivial to start getting to 6.9s, because it's not. But hopefully these patterns that you're seeing here, you can start to see how, as you start thinking through them, you can start hardening the system and start handling more types of failures and sort of build kind of reliability across them. There's a reason why for Azure we always try to have 2 regions inside each geopolitical boundary. So when we come to Australia, we'll have 2, one in New South Wales and one in Queensland, is so that for you inside New Zealand, you can access both of them with good latency, and you can do that failover, and you can actually have your services distributed across the 2 in order to do these types of tricks and drive your SLAs up. Cloud services, I'm just going to briefly mention, is one way you can package up these apps in order to actually have both your web and back-end tier set up together. So I think we're out of time, but hopefully you saw here a bunch of different patterns. I kind of touched briefly on them, but hopefully enough that you can start to see how they compose and fit together and some of the things you want to think about. To learn more, recommend a couple of different resources. The first 2 here are a bunch of great videos and white papers that we've produced at Microsoft. I think we have like 25 hours of videos on this fail-safe stuff. It goes into a lot more depth, a lot of code, a lot of samples you can walk through. I would say some of it's probably overkill for some apps, but if you're just building kind of an enterprise non-mission critical solution, you probably don't need to go into all 25 hours of videos. Having said that, if you want to build the next trade meet, you probably would. And so the good news is we've got all that content there. We also then have, there's 2 books, one that's based on Azure by Bill Wilder, one of our MVPs, that's really good. There's also one called Release It, which is just a good book in general about running production service systems that you can read. Everything I've shown here, you can sign up on windowsazure.com and start using. And hopefully got you excited a little bit with cloud computing this week. There's a lot of cool things you can do with it. It's also a lot of fun as a developer. And if you follow these patterns, you'll be even more successful if you build with it. So thanks a bunch. Have a great week.